Okay, hello. So this is chapter 6 about the normal distribution. So this chapter is particularly important for the later chapters. It's a preliminary chapter to do our inference and like estimation, hypothesis testing. Everything in the following chapters are is based on the results we study from this chapter. So from this chapter and on, everything is interrelated. So please pay more attention to understand what's going on. So as I said in the previous chapter, we learned parametric distribution family, and there are a lot of parametric distribution models, but in this course we will just learn only two of them. One is the binomial distribution, which was covered in chapter 5, and the other is the normal distribution from this chapter, which we are going to learn in this video. And as I said, the normal distribution is the single most important distribution in not only in statistics but in any science, social science, natural science, whatever. So among any distribution, the normal distribution is the most important one. I believe if you ask anyone, any statistician, any scientist, whoever, I believe they would agree with that. So, and it is clear from the name. It is called normal. So it is normal. This distribution is normal. That means anything else is abnormal. So the name is pretty striking, like a surprising name, but it's accepted. So that means how important this distribution is. So, and I'm saying it now. The every random variable, every single randomness from this chapter and the following chapters will be approximated to a normal distribution. So from now on, the normal distribution is the only distribution we are going to use. So as a variant or in as a side note, I may mention a few other distributions from time to time, but basically when you need to calculate a probability, it will be based on the normal distribution. So that's the importance of this chapter and the theory of the normal distribution. So okay, and textbook chapters, just search for normal distribution. Then you will see a lot of references, information online and textbooks, anywhere you can find the references. Okay, let me start with warm-up question. So I'll give you 5 random variables, and you find one that is different from the others. So the 5 random variables are: first, A, the exact amount of a tall size coffee, and B, the time when a bus arrives at a bus stop, C, the weight of a wild-caught salmon, D, the speed of a randomly chosen car on highway, and E, the number of traffic accidents on a random day. So those are all random. They could be different from time to time. So all are random, but one of them is a little bit different. Oh, by the way, there is no correct answer. I'm just giving you one example. So the answer is E, the number of traffic accidents on a day. So the difference I the intended answer is E, and the reason is that E is discrete because it takes on a countable number of values. That means integers. So the number of traffic accidents cannot be a negative number, nor it cannot be like fractions, decimals. Like it should be 0, 1, 2, 3, 4. Like it should be integers. So we call such a variable discrete random variable. Discrete. It takes on the discrete points. On the other hand, the other four random variables are continuous in that they can take any value, any real number, right? Any number on a possibly unbounded interval. Like, for example, the amount of tall size coffee at a Starbucks. Say you ordered a coffee, but and even though it's tall size coffee, maybe say it's 12 ounce, but like actually, if you measure that coffee with a scientific like scale, then the amount could be different from exact 12 ounce, but it can be like 12.01 or 11.99 ounce. So basically, any number is possible, right? Any number around 12 ounce would be the possible outcome. And B, the time when a bus arrives. Suppose that a bus is supposed to arrive at noon, but it can be late or come early by, like say, by 1 second, 2 seconds, or 0.1 second. If you measure that with a scientific timer, like if you measure it with a super accurate timer, then like it can be any time. So and the time is on interval continuous timeline. So the outcome could be any point on a timeline. Similar weight, speed can be like the weight of a salmon could be say, I don't know how big a salmon is, say 1 pound, 2 pounds can be possible, but also 1.1, 2.9. All the numbers are possible. Speed is same, like 60 miles, 60.0001 miles. So now I hope, like now I guess you understand the difference between continuous variable and discrete variable. So if a variable takes a countable number like 0, 1, 2, 3, then that's discrete. But if a variable can be any number, like on a certain interval around a certain line on a certain interval, then that's continuous. So I'm giving so now in this chapter we are going to focus more on the continuous random variable. So far most of our examples are based on discrete random variables because discrete random variables are easier to understand, easier to handle. But now like we are going to study how to handle the continuous random variable. The big difference is the big difference between continuous random variable and discrete random variable is that a continuous random variable has no fixed increment. So discrete random variable has a fixed increment. So if you choose two outcomes next to each other, then there is no possible outcome between them. But a continuous random variable is literally continuous. So no matter what two outcomes you choose, there is another possible outcome in between them. Like for example, if you choose point 0.000001 and 0.000002, still there is another number in between them. No matter what two numbers you choose, there is another number in between them. Always you can make up another number that lies between two numbers. So that's a difference between continuous random variable and a discrete random variable. And then the problem, like so, think about this. It makes the problem more complicated. So we are going to use the bus arrival time as an example, running example, to introduce you the idea. So think about that. You are waiting for a bus at a bus stop, and the exact moment the bus arrives in front of you is a random variable. It can be late, it can be early, so it's random, and you are measuring the time with the super accurate watch. So now we need to study the distribution of the arrival time. And based on our previous approach that we considered from chapter up to chapter 5, then our approach was to list all the possible outcomes, and we assigned probabilities. So we made a probability distribution table. So by making a table, we could describe the full probability distribution. That was possible because we could list all the possible outcomes. However, now that is not possible. When you list two outcomes, then as I said before, there must be another outcome in between them. So you can find another outcome in between any two lines. So it is impossible to list all the possible outcomes. There are uncountably many outcomes, like there are uncountably many time moments within a time interval. So our approach is not applicable. That's the problem. When you handle a continuous random variable, you cannot make a table with all the possible outcomes. So we have to use a different way to define and describe and present the probability distribution. That's what we are going to do before we begin the normal distribution. Excuse me. So then this is another way. Instead of listing the outcomes as a table, we are going to use a line. So suppose that the bus is supposed to arrive at noon, so 12 o'clock, but it can be early or late, say by up to 10 minutes. So that's the maximum error in the bus arrival time. And then we are going to describe the probability distribution using this timeline, right? Think about this timeline. So we know that the bus arrives between plus minus 10 minutes around noon, right? So there is 100%, it's 100% that the bus arrives within this 20-minute time window. So that's our starting point. Then we are going to assume that this is one possible way to describe the probability distribution. We are going to assume that the probability is proportional to the length of time interval. This is possible. So if you make an assumption that the bus can arrive anytime within these 20 minutes, then, for example, you can calculate the probability that the bus arrives within plus minus 5 minutes. That would be 50% because the time window is half of the 20 minutes, 100% window. So the probability is proportional to the length of the time interval. So it's natural, and length is exactly a measure of uncountable measurement. So length is a line is not countable. Line is composed of infinitely many dots. If you put a lot of dots, if you connect them, then it will make a line. But there are infinite number of dots within a line. So it cannot be counted. It cannot be listed. However, still you can measure the length. Probability for a continuous random variable is similar. It cannot be counted, but still we can measure it like a length, right? So I like then as I said, you can calculate any probability under that assumption. If you understand the probability is understood as a length, then you can calculate any probability. So this is an example. What is the probability that the bus arrives between plus minus 2 minutes? Right? It's simple. That window, this window is 4 minutes window. Its length is 4 minutes. And 4 minutes is 1/5 of 20-minute whole interval. So the probability should be proportional. The probability is 1/5, which is 20%, right? So 20 minutes has 100%. Then 4 minutes should have like 20 minutes. Or you can understand each 1 minute has, for each minute, there is 5% probability. So 4 minutes has 20% probability. Right? So this is an example of how we are going to describe the probability. So like when I say the probability is proportional to the length of time interval, then it's all done. So you know how to calculate the probability. But let me ask you another question. Think about another question. Then what is this? What is the probability that the bus arrives exactly at noon? Exactly on time means like it should be exactly 12 o'clock with 0 second. It cannot be late or early even by say nanosecond. Your watch is super accurate, so it does not allow any error, right? Think about this question, and I'll come back in the next video with the answer to this question. So see you later.